Okay, so let's do an application. Let's suppose I know that blood pressure. I know that blood pressure has no distribution. It has mu that I don't know, but it has a sigma that I know is equal to, let's say, 50. Okay, and I am interested in estimating this right here. So what I did is I got a sample of n, let's say, to 25 individuals, and that gives me an average blood pressure that is equal to, let's say, uh, 128. While 128 is a very good point estimate, it remains a point estimate. I can do better than that by creating confidence. And if you remember, we said that the confidence interval formula is basically the point estimate, which is x squared, and you build around it by adding and subtracting. Is that value, and that value is going to depend on how much confident you want to be, and then you're going to multiply it by the standard error, يعني sigma over root square of n. Okay, so question number one, you're asked to calculate 95% confidence interval. Now to calculate a 95% confidence interval, you're going to apply the formula. You take your xy, which is 1, and then you're going to add, and you're going to subtract. Now, it's a 95% confidence interval. That value is going to be replaced by 1.96, and you're going to multiply by the standard error, which is sigma, that you already know is 15, and it's divided by the square root of the sample size, which is square root of 5. Okay, so that means 128 minus 1.96 and 15 divided by 5 is 3. So this piece right here is going to be about 6. It's a little bit less than 6. I'm not talking exactly. Equal to 1.96 multiplied by 3, you get 5.88. So, meaning that the 95% confidence interval is okay. So you're going to take the 128, you're going to subtract 5.88, and that gets you to, I want to make 112.12. That's the lower limit, 112, all the way up to, now you're going to take the 128 and you're going to add this time 5.8. The answer is 136.88. 136. By doing so, you've answered the first question, which is calculate a confidence interval. Now, the second thing that you're asked is how would you interpret? So, interpretation, um, let me make it bigger so I can see it. Okay, so the way we do the interpretation, we say we are 95% confident. Not 95% because that's what we're calculating, that the population, and notice I said population, average blood pressure, and I'm talking about you, is somewhere. I don't know exactly where, but it's inside the interval, so somewhere between 122.12 and 133.88. Therefore, it could be 125, it could be 130, I don't know, but this is my best shot at interpreting this confidence. Now, here's the third thing that can happen. If somebody comes and say, well, we have reasons to believe that the population you studied is actually the population of people that are hypertensive, meaning they're trying to tell you that the mu is actually equal to 140. This is what we're trying to tell. Well, if you remember, based on the calculation you did, you are 95% confident that U is between 122.12 and 133.8. Therefore, this suggested value is not accepted. And therefore, based on the confidence interval that you just calculated, you can say that I do not agree with this value. This value doesn't seem to be reasonable. Therefore, I'm going to say no. I believe based on the sample, based on the calculation, mu is not equal to 140. Okay? Because as you can see, mu is not included in the confidence interval. Only values included in the confidence interval are acceptable. So though you do not know if mu is equal to 122.5, 123, or it could be 125, or it could be 128, or one, you don't know. But if you're provided with values that are beyond the limits, you can kind of like argue that no, I'm not going to accept it. Okay, so now you have a good understanding of how confidence intervals work. First, you get a point estimate, then you build around an interval. Third, you do the interpretation by saying we're 95% confident. We don't say we're 95% sure. We don't say that. By the way, هلا حاعطيكم شوية interpretations that are wrong. So we say we're 95% confident that the population average is between these two values. A wrong interpretation is to say we're 95% confident that the sample average is. You're not drawing interpretation about the sample average. You know the sample average is right there. You know it. You don't need to do any type of estimation. So that's wrong. The other thing that is wrong is to say that 95% of the averages is between 1.22 and 133. No, that's not what we're doing. And also say that the population average fluctuates between. No, the mu does not fluctuate. Mu is a constant. Mu is one value. And all you're trying to do is you're trying to estimate that value. Now, you can do a point estimate by getting a sample X bar. You can do an interval estimate by building the interval around that estimate. Okay? Now, having done this example, let's go a little bit further. All right, so we said that the confidence interval works by getting X bar, and you add, subtract that value, multiply by the standard error. That will give you the confidence. Okay, now you already know that if you are interested in getting a 95% confidence interval, then that has to take a value. Now, but what if you're interested in building a 99% confidence interval? Well, that has to take a different value. Now, what is this value? Well, it's not that hard actually. What you need to do is you need to go to your Z table. Actually, go to your T table. Now, remember how the T table, the last entry I told you, this entry is actually a Z value? Okay, remember that. Now go all the way up. Now, so far in the T, we've been using this row of values, yani what is called one-sided. Now, with the confidence interval, we're going to use the two-sided. Now, 95% confidence interval, you go to the area 95%. And if you keep on that column and go all the way down, well, notice what value you get, the 1.96. This is exactly that value we're looking for. Therefore, using the same logic, if I want to build a 99 confidence interval, I go to the two-sided, بعدني بدي, it's fine. I go to the 99, and now I'm going to go all the way down till I reach the Z, and the values I have to plug in is 2.5758. Therefore, that is 2.5758. Okay, now what if I'm interested in 90% confidence interval? Okay, well, same approach. If you're interested in 90% confidence interval, go to your T table, and this time pick the two-sided, find the 90%, and scroll all the way down till you reach your Z. And here's your Z, 1.6449. 1.649. Okay, great. Now notice what happens. As you go from 90% confidence to 95% confidence to 99% confidence, that value is growing bigger and bigger and bigger. يعني كل ما you want to be more confident, the Z is going to be bigger. Therefore, if the Z is bigger, then this entire value right here, this is called the width or half of the width of the interval. If you multiply it by 2, you get the width. So if the half of the width gets bigger, yani the width of the interval gets bigger. Now, if the interval is wider, is it more precise or is it less precise? Well, think about it this way. If you're meeting somebody and that person says they're going to meet you at a place between 8 and 8:05, then they give you an interval of 5 minutes. Versus if they say, well, I'm going to meet you between 7:30 and 8:30, they give you an interval of 1 hour. Well, which of the two is more precise? Obviously, the narrower one is more precise. Again, another example. If you ask me what grade you're going to get on your midterm, if I tell you your grade is between 60 and 100, versus if I tell you your grade is between 80 and 82, when am I being more precise? Obviously, the second time, when I said your grade between 80 and 82, I'm being much more precise than when I said between 60 and 100. Therefore, when the width of an estimation becomes wider and wider, like the case here, then you're going to lose precision. Okay? So, though you gained confidence, you gained from 90 to 95 to 99% confidence, you lose on the precision. And this is typical. I mean, again, think about it. If I tell you, like, how confident you are you're going to get between 50 and 100 on this, versus how confident you are you're going to get between 85 and 88. Obviously, you're much, much more confident that you're going to get between 50 and 100 than you're confident that you're going to get between 80 and 84. So it makes sense, and actually calculation-wise it works. All right, so that's one of the things that affect your confidence interval is how much confidence you want. The more confidence you are, the bigger is your set value, and therefore the wider is the interval, and then you lose on the precision. Like, what about is there anything else that is affected in this confidence interval? Well, look at sample size. What happens is when your sample size increases. When sample size increases, the standard error, now by now you know that this is the standard error decreases. When the standard error decreases, the width of the interval decreases, and the precision, therefore, increases. Okay? So I think this is maybe the third time we look at the effect of sample size. Sample size increases, the width of the interval decreases, yani the interval becomes narrower and narrower, and therefore you become much more precise in your estimation. Okay? So, to recapitulate, when you're doing a confidence interval, um, you do it by getting your endpoint estimate, and you build around it an interval which is made of two parts. The first part is Z multiplied by your standard error. If you want more confidence, your Z value is going to increase, and therefore the width of the interval is going to increase, and the precision is going to decrease. On the other hand, if you increase your sample size increases, then your standard error decreases, and therefore the width of the interval decreases, therefore the precision increases. Okay? Now, what we have been saying so far about the Z and the T apply here, meaning that to be able to use this formula, the sampling distribution of the mean has to be normal. Okay, so to be able to use this, SDM has to be normal. Either X has to have a normal distribution, or n has to be greater than or equal to 25. Okay, so whether you're using the Z or using the T or using the confidence interval, you're still stuck with the same requirement. SDM has to be normal so that you can use it. Okay, all right. Now here's when it's going to get a bit fun. So X letter, which is sigma. Wonderful. Well, remember when we introduced T and sometimes we do not know sigma? Well, same problem. What happens if I sigma? Solution. Sigma, you replace it by its sample estimations. You're going to replace it by S that you get from the sample. But automatically, same as we did with the Z, you no longer multiply by Z because it's no longer a Z distribution. It becomes a T distribution with degrees of freedom equal to n minus 1. Now, how do you get this T? The same way you get that. You go to your T table down here. And so if you're interested in 95% confidence interval, you pick again two-sided 95. And then you go down depending upon the degrees of freedom that you're working with. So if you're working with degrees of freedom 20, then you're going to stop here and you're going to take the value 2.0860 and you're going to plug it in here. And that will get you. That's again, we're going to stick the pressure has a normal distribution with a certain mu and a certain sigma. But this time we do not know mu and sigma. So we took a sample of n equals, make it easy, 9, and the x bar came out to be 170, for example. Okay. And I got an S that is equal to 20. And you are asked to calculate a 95% confidence interval for that mu. Well, the formula says you take your x. First, before we continue, is the SDM normally distributed? Yes, it is. Why? Because actually blood pressure, the original solution, is normally distributed. All right, so let's apply the formula. You take the x bar, which is 117. You add and you subtract t. Now I need to get the t, but first of all, is the degrees of freedom for that? N minus 1. N is equal to 9. Minus 1 is 8. And I'm looking for 95% confidence interval. So I go to my t table. 95% on the two-sided. I'm going to go for degrees of freedom 8. Degrees of freedom 8 gets me 2.3060. So that's the value I plug in. 30, 60. And then I'm going to multiply by the standard error using S this time because I do not have sigma, which is 20. And 20 is divided by the square root of 9. Yani, okay. Now this whole piece is going to be equal to 2.3060. I'm going to multiply it by the standard deviation, which is 20, and I'm going to divide by 3. That gives me 15.37. Quite large, but therefore, my confidence interval, I'm going to do 117 minus 1537. That will give me 1.63 all the way up to, I'm going to add 132.37. Okay, so that is my 95% confidence interval. How would I do the interpretation? I would say we are 95% confident because we're doing 95%. population mu, يعني the true population blood pressure average, the average of the population is somewhere between 101.63 and 132.37. Okay? I don't know if it's 110 or if it's 122. I don't know. All I know it's between these two values. Okay. 3, if for some reason somebody is suggesting that the mu is equal in this population to 115. Okay, so this is the value that they are suggesting. And now you want to reflect if you accept or you don't accept this value. Well, look at 115 and compare it to your confidence interval. Is it inside your confidence interval? Yes. So actually, the value, it could be true. So that's what you say. Well, I cannot argue against it. I cannot reject it. Therefore, I'm just going to say, well, it looks like this is an acceptable value, and I'm just going to go with it. Okay. So I'm hoping that this is a good introduction to confidence interval. You can try to do the the assignment and see if you can actually answer the question.